All right, so how'd you do with this function? It's not rational, so you don't have the chance to cancel the numerator and denominator, but you can still pull the highest exponent. Here's the idea. The highest exponent will always dictate what the graph is going to do when you go to infinity. So it's kind of like this stuff over here, this minus 3x squared, this plus 1. It has a minimal impact on the behavior of the graph. Okay, so whatever 2x to the fifth is going to do is what this whole function is going to do when we talk about the limit. So again, I kind of ask you, what do you think about this limit? We actually haven't done it yet. Okay, we didn't do it yesterday. You haven't seen the limit of something like 2x to the fifth. What happens if you have a really big x value, which is kind of like infinity? What happens if you have a really big x value and you raise it to the fifth power? What happens if you have a bigger x value than that and you raise it to the fifth power? And then a bigger number after that. If you keep raising something to the fifth power, what height, what y value do you get to? Infinity. Okay, it's okay to have an answer like that. It's actually the second time that you've seen the answer being infinity. Now, when we say that the answer is infinity, what that's really describing is that the y value just keeps getting bigger and bigger. Just so you understand, that by limit definition is not an intended height. Again, infinity is not an intended height. So we can also say does not exist. Now, kids start to catch on. They're kind of like, so which answer do you want me to give? I want you to understand that each of these answers is kind of saying its own thing. So this is saying that the y value just keeps getting bigger and bigger. This is saying that there is no intended height. Both of those are the same idea. Okay, so that's why we can give both answers. Honestly, when it comes time for a test or quiz, you could give either answer. Okay. Now, in the last, I think, 4 problems, we've had what I like to call a recognizable expression. To recognize these expressions will help you to get the answer right next time you see it. So now you've seen these, but some people like to put them in its own space. It's just that I showed them to you through 4 or 5 examples. So first of all, if you have something like 1 over x, that kind of goes back to that conversation. 1 over x is going to get divided up so much. 1 over x is going to get divided so much that it's going to approach 0. Okay, so we recognize that. Now, we sort of have a little spin-off of it, where I hope that you would say, yeah, Ms. Nail, it doesn't have to just be 1 over x. It could be a over x. A implying any number. Okay, now those 2 statements should kind of taste like this problem, where we basically discovered that we're dividing by x, and that's going to get closer to 0. In other words, the intended value is going to get closer to 0. Here's one from yesterday, sine of x over x. We didn't do anything with it today, but it's worthy of repeating. Now listen, there's some things in math that you're going to have to memorize, but I don't want this to be just a memorized thing and you don't have any idea what it means, because then you forget it. So sine of x over x, that's a graph. It's kind of a weird graph because it does this. And as it does this, it keeps dampening until it gets closer to a y value of 0. So we're picturing that graph that is slowly but surely getting closer to 0. Okay, that's really what that statement means. This popped up today. The limit of a number, the limit of a constant. We usually use the letter C because it's to represent a constant. So again, What's the intended value of a constant? Well, it's always going to be the same. It's always going to be c. Okay, even if you go to infinity. Now, are you kind of noticing, or are you wondering, like, what's up with like the negative infinity? You can see here that we have plus or minus. Okay. The reality is that whether I have a plus or minus, each one of these is going to be the same limit, because if I go to the right or if I go to the left, I'm going to be approaching the same height. Okay. So that's why I'm able to say that. But you might notice up on the board here that we kind of just focused on the positive side, which usually we'll just do the positive side when we're talking about not using a calculator. So we'll just kind of think of it generically as positive infinity. Again, when you don't have a calculator. How about this one? Okay, x to a power. X to a power. Are you sort of picturing it? I mean, what happens when a big number gets raised to a power? Okay, we have the same conversation that we had for this problem. Okay. By the way, any graph of x to a power, which we didn't talk about the graph of this one, and I kind of wanted to, if you want to add it to your notes or just look at it, but it's always going to look like a graph that just goes up, up, and away. Okay, so any power is eventually just going to keep going up, up, and away to no y value. Okay, so these 5 expressions, and I'll say derivations of them. A derivation would be something that is of the same idea, is always going to have that limit. Okay, we're picturing either what the graph is doing, or we're picturing what would happen if you think about big numbers. And that's why they will always come out to be these answers. One more slide, and then I'm actually going to give you guys like a couple problems to practice, and even ask you in some small groups to sort of be an expert. And we're even going to get them up on the chalkboard as just a little activity. But I want to show you one more slide to sort of just put, oh, I forgot. No, nobody asked, but I still could have said, frowny face implied this, but I really should say that. Okay, frowny face meant does not exist. Okay, it's something we've been saying. I just want to put it in print, because when you see it, then you realize it's important. So a horizontal asymptote and a limit. Okay, again, they are the same idea, and you can use an end behavior model to find either one. Okay, basically exactly what we did with these problems this afternoon. We can use an end behavior model to find either one. Okay, because again, they're basically the same thing. Okay, now let's do this. I like doing this when time allows, because really this is when you start to think. I'm going to give you 4 problems. Try them, tinker around with them, try to get the answers without a calculator. Okay, now eventually we're going to say, hey, why don't you kind of be the expert for this problem? And usually it's kind of interesting to listen to you guys explain these. Okay, so here's 4 limits. Give yourself some space in case you decide to skip one of them. And then if you're comfortable with it, I'd like to give little groups of 3 just kind of assign you one of them to see if you can specialize in its answer.